We're looking at Chapter 5, Polynomial Functions. Specifically, we're looking at Section 5.2. In this lesson, we'll look at how to identify the characteristic of a polynomial function using its equation. So we'll be looking for mainly the y-intercept and end behavior. If we recall the polynomial functions we looked at in Section 5.1, we have a constant, a linear function, a quadratic function, and a cubic. A constant is of degree 0, a linear of degree 1, quadratic degree 2, cubic degree 3. The sketch of the graph, of course, a constant is a horizontal line, a linear is an oblique line, a quadratic being a parabola that can open up or it can open downward, and a cubic is a sideways S or a backwards N or a stretched out N looking graph. The number of x-intercepts for each one of these functions. For a constant, there will be 0 x-intercepts except for the function where y is equal to 0. That is, the line would be the x-axis. And in this case, there will be, every point would be on the x-axis. For the number of x-intercepts for a linear, there's 1 x-intercept. For a quadratic, there could be 0, there could be 1 x-intercept, or there could be 2, a maximum of 2, of course. A cubic would have 1 x-intercept, or 2 x-intercepts, or 3. Of course, the degree tells us, the degree of a function tells us it's the maximum number of x-intercepts. The number of y-intercepts for each of these functions would be 1. The end behavior for a constant, the line extends from quadrant 2 to quadrant 1, or from quadrant 3 to quadrant 4. So from quadrant 2 to quadrant 1, or from quadrant 3 to quadrant 4. In a linear, the line can extend from quadrant 3 to quadrant 1, quadrant 3 to quadrant 1, or from quadrant 2 to quadrant 4. For the end behavior of a quadratic function, the curve would extend from quadrant 2 to quadrant 1, or from quadrant 3 to quadrant 4 if it opened downward. In a cubic, the end behavior will be the curve would extend from quadrant 3 to quadrant 1, which would be something like this one here. It would eventually get in quadrant 3, or from quadrant 2 to quadrant 4. The domain for each of these functions is a set of real numbers. That means x could be anything. For the range of a constant would be that number, of course, because every y value would be the constant. For a linear, as y belongs to a set of real numbers. For a quadratic, it varies between if the graph opens downward, then there will be a maximum point, such as this one opens down, and hence the range would be, in this case of the red graph, it would be 0, less than or equal to 0. And if the graph opens up, the range would be at its minimum. For example, right here of the green one, the range would be from here and greater than or equal to your minimum point. For a cubic, we're back to y belongs to a set of real numbers. The number of turning points for each of these polynomial functions. For a constant, there is 0. I recall that the number of turning points is how many times the graph would go from increasing to decreasing, or decreasing to increasing. A linear also has 0. A quadratic would have 1 turning point. For example, decreasing to increasing, or increasing to decreasing. And in a cubic, it would have 0 or 2. So we're going to look first at the leading coefficient, and it's the coefficient of the term with the highest degree in the standard form of a polynomial. The important thing here is that when you're looking at an equation of a polynomial function, the leading coefficient will help us determine the end behavior. So here are some examples. We have first we have a function, a linear function. We know it's of degree 1, and our leading coefficient would be -2. This should tell us that the graph, just do a little sketch of the graph here. The graph would look something like this, and that means it would go from quadrant 2 to quadrant 4. In the next case, we have a cubic, a function of degree 3, and the leading coefficient would be 3. That means a would be greater than 1, or sorry, greater than 0, rather. And in the last function, we have a function of degree 2, which is a parabola, a quadratic function. And in this case, our leading coefficient would be -1. This would be a is less than 0. So that's how to identify the leading coefficient from an equation of a polynomial function. So what does this tell us about the end behavior? So if we have a linear function where a is greater than 0, that would be an increasing function. That would be an increasing function. Something like f of x is equal to 2x plus 1. 2, of course, being greater than 0. And the end behavior of this would go from the graph, the line would go from quadrant 3 to quadrant 1. Would look something like that. We may also have a linear function where a is less than 0. And in this case, this would be a decreasing linear function. Something like f of x is equal to -3x plus 4 would be an example. This being -3, the a value being -3. And we could see that the end behavior of the line here would be quadrant. It would go from quadrant 2 to quadrant 4. The graph would look something like this, going this way. In a quadratic where a is greater than 0, this would give us a quadratic function that would open upwards. Something like f of x is equal to 2x squared plus x subtract 3. And of course, that would go from quadrant 2 to quadrant 1. The graph would look something like this, open upwards. If a is less than 0, if the leading coefficient is less than 0, means there's a negative leading coefficient, then that means the quadratic function would open downward. And a function would look something like, would have a negative leading coefficient, so it would have something like -x squared plus 3x subtract 4. And that will go, the end behavior will be from quadrant 3 to quadrant 4. Something like this. In a cubic function, and I would call this an n-shaped function. If a was greater than 0, we would have something like f of x is equal to x cubed plus x squared plus x plus 1. And that will take us from quadrant 3 to quadrant 1 for the end behavior. Looks something like this. And of course, a cubic where n is less than 0 will give us a negative leading coefficient. And I call this a backwards n shape. It's something like f of x is equal to negative 2x cubed plus 1. Sorry, 2x cubed plus 1. And that will, the end behavior of the curve will be from quadrant 2 to quadrant 4. Something like that. If you recall that a linear function and a cubic function will have odd degrees, and you see that they will end, their end behavior would be in opposite directions. Their end behavior will be in opposite directions. One will start down, the next one will start as an increasing, one will start increasing or end down, whereas a quadratic function has an even degree, and they start and end in the same direction. Another characteristic that we're going to look at in the equations of polynomial functions will be the constant term. And the constant term in an equation provides us with the y-intercept, that is when x equals 0. So we have a constant term in this cubic function. The constant term would be 1. So the constant term here is 1. That means that there's going to be a y-intercept at 1. Here in a function of degree 2, quadratic function, we have a constant term of 0. And here, of course, in a linear function, we have a constant term of 1 again. Let's look at an example. We have a function, a polynomial function here of the 3rd degree. It is a cubic. And as we recall, cubics have a set of reals for their domain and for their range as well. The y-intercept of this one will be our constant term. Constant term tells us the y-intercept. And in this case, the y-intercept is 1. Or we could write it as a coordinate 0, 1. The leading coefficient is the coefficient of the term with the highest degree. This will be this one. The leading coefficient is 2, which gives us an end behavior. A will be greater than 0. So our graph will be shaped as an N as such. And that will be going from quadrant 3 to quadrant 1. A little sketch, it would look something like, we have to have a y-intercept of 1, maybe something like this. The turning points, of course, the maximum number of turning points will be 3, rather 2. The maximum will be 2 turning points. There could be 0 turning points or 2 turning points. The maximum number of x-intercepts would be 3. If you'd like, you could pause the clip and try this example on your own. For this function, a linear function, the degree will be 1. Of course, the domain of a linear function is x belongs to a set of real numbers. The range, y belongs to a set of real numbers. The y-intercept is our constant term. And so we have a y-intercept of 1 again. The leading coefficient is negative 2, which means that A is less than 0. So we have a decreasing graph. It would look something like this, decreasing. And so the decreasing, the end behavior would be quadrant 2 to quadrant 4. The number of turning points, or the maximum number of turning points in a linear function, would be 0. And the maximum number of x-intercepts would be 1. So this is popular. We can give you any function, polynomial function, and ask you any of these questions as a multiple choice or a short answer question. If we look at another example, once again, you may want to pause the clip, attempt it on your own. We have a quadratic function, which is degree 2. The domain being x belongs to a set of real numbers. The range of a quadratic function is very specific. We'll just come back to this one right now. The leading coefficient of this one is -2, which means that A is less than 0. So it means that it would open downward. That gives us the range being y is less than or equal to its maximum. And the end behavior would be quadrant 3 to quadrant 4. The number of turning points in a quadratic would be 1. And the maximum number of intercepts, x-intercepts, would be 2. Here's another example. We have a function of degree 3. Range, y belongs to a set of real numbers since it's cubic. The y-intercept, of course, is the same as the constant, which in this case is 1 again. We have a leading coefficient of -1. That means A is less than 0. So we have a backwards n-shaped graph. And that means the end behavior will be quadrant 2 to quadrant 4. The number of turning points, the maximum number of turning points, is 2. Of course, it could also have 0 or 2 turning points. The maximum number of intercepts would be 3. Here's very common. We can match a equation to its graph, match a polynomial function with its graph. And so we have 6 graphs, 6 equations. Here we have a linear graph, which could only be h of x or q of x. Both of the linear graphs are decreasing, as both the leading coefficients are less than 0. So in order to tell these equations, we're going to have to look at the constant term for the y-intercept. And we have this one. The first graph has a y-intercept of -3. So we have -3 here. And we also have -3 here. This has a slope of 1/2. This one having a slope of -2. So that one would be steeper. So we have this one is, the first graph would be q of x, since the slope is steeper than the one with 1/2. This would be h of x. We have graph number 2 right here is a quadratic. It is a function of degree 2. We can look at this one, and we have also a function here, degree 2. Both open up, so the leading coefficient will not help us out here. Both of these graphs open up. So let's have a look at the y-intercept. This one has a y-intercept of -2. So we have that's a cubic. Here we have a quadratic function of degree 2 with a y-intercept of -2. And this one has a y-intercept. It's a quadratic equation, but it's a y-intercept of 1. So we have this one being j of x. And of course, this will be k of x. We have left two cubic functions. One is an n, the other one is a backwards n. So the leading coefficient will help us out here. If we look at g of x, we have a negative leading coefficient. If we look at p of x, we have a positive leading coefficient. A positive leading coefficient will give us an n. So this one will be p of x. And a negative leading coefficient will give us a backwards n, g of x. Here's another example, something you could see in a constructed response item. Right, give an example of a polynomial equation with each of the characteristics. So it extends from quadrant 3 to quadrant 4. It would have one turning point. It'd have a y-intercept of 4. So if something extends from quadrant 3 to quadrant 4, and if we look at the quadrants, 1, 2, 3, 4, that means it would start here and end here. The only function that we studied would be a quadratic. So we have something, f of x has to be a quadratic, and it has to have open downward. So it has to have a negative leading coefficient. So let's use -2x squared. Has one turning point, which also identifies a quadratic, and a y-intercept of 4. So that is one example. Of course, there are many examples as long as you have a leading coefficient, a negative leading coefficient to satisfy this part, and the y-intercept of 4. Next, we're going to look at a increasing function of degree 1. This tells us there's a linear and a y-intercept of 4. So we have f of x. An increasing function means that it will that we have a positive slope. So we could have 3x would be an increasing function plus 4. In our next one, we're looking for an example of a function that has a maximum of 2 turning points. A maximum of 2 turning points would be a cubic. So we could say 3x cubed plus 3 would give us a maximum of 2 turning points. So in summary, we looked at 4 polynomial equations and what each part in their equation would give us. For a constant, if we have a leading coefficient of a, there is no leading coefficient. For a linear function, we have the leading coefficient, of course, tells us the end behavior. And for a linear function, if a is greater than 0, then we go from quadrant 2 quadrant 3 to quadrant 1. If a is less than 0, we go from quadrant 2 to quadrant 4. And the shape of the graph, if a is greater than 0, the shape of the graph would look something like that. If a is less than 0, the shape of the graph will be a decreasing function. The constant term, as with any polynomial function, the constant term will give us the y-intercept. The shape of the graph of A horizontal function would be of a constant would be a horizontal line. Something like this. And the constant, of course, would also be the y-intercept. When looking at a quadratic function, the leading coefficient will also tell us the end behavior. And if we have a is greater than 0, our end behavior would be quadrant 2 to quadrant 1. And if our a is less than 0, the leading coefficient is less than 0, we would have from quadrant 3, it would open downward to quadrant 4. So for the shape of the graph, for a is greater than 0, you're going to see it open upward. For a is less than 0, it would open downward. And of course, the constant term will tell us the y-intercept again. When we're looking at a cubic, a function of degree 3, the end behavior, if a is greater than 0, we're going to see an N-shaped. And of course, that will go from quadrant 3 to quadrant 1. And if a is less than 0, it will go from quadrant 2 to quadrant 4. The shape of the graph, if a is greater than 0, you'll see an N or a stretched out N. If a is less than 0, you'll see a backwards N or a stretched out backwards N. Some people call it a sideways S. We have the y-intercept will be given to us with the constant.